just want to explain what a chemical equation actually is, and it's just the shorthand representation of a chemical reaction. You've seen them before. We dealt with it actually with our first lab, with our burning candle lab. And chemical equations always have the reactants on the left side and the products are on the right, with what we have is our yield sign in between. Now, in our actual word problems or sentences that we're going to see, we might end up looking at seeing yields, produces, forms, or makes. Any of those four words mean yield sign, and it means that we have our reactants, and we're either yielding, producing, forming, or making our products, what we end up with. They also include our states of matter, and lastly, they include our catalysts. The catalysts actually go above the yield sign, and that's because they're important to our chemical reaction, but they just speed it up. But they actually aren't consumed, so they're not a reactant or a product. And so we just place them right there, and an example of that would be heat. And you can see that's represented by the delta sign. So our states of matter are going to be solid, liquid, gas, or aqueous. Now, we all know that you're familiar with solids, liquids, and gases, and we represent those, if you can point Ms. Frankovic right there, like a sign like that after each of our chemical formulas. And so for our solids, those are going to be all of our ionic compounds, ice, and our metals, except for obviously mercury, because that is our one exception at room temperature. It is a liquid. That brings us to our liquids. Remember, bromine, also an exception. It is one of our 7 diatomic elements, but it is not a gas. It is also a liquid at room temperature. Water is going to be our other liquid that we are dealing with. You'll note that there's not many things that are liquids, and that's basically, thank you. That is basically the only 3 things that you would ever write with an L afterwards. Otherwise, if we do have a solution, it is going to be aqueous, okay? So those are things that are going to be dissolved in water. Now, we are dealing with those a lot. We deal with a lot of aqueous solutions. Ionic compounds in particular get dissolved in water and break apart into their 2 component ions, and also our acids that we went over in class already today. And lastly, we have our gases. Our gases are going to be all of our noble gases, and our 7 diatomic elements are going to be always represented or in a gaseous form, and also water vapor, which we also sometimes refer to as steam. Same thing. So as you can see, water can be found in any state in our equations that we're going to be looking at.
And remember, those diatomic elements diatomic molecules are the hydrogen, oxygen. I'm not doing these in order, but I should. Bromine, iodine,
chlorine, chlorine,
and chlorine.
And nitrogen. Yeah, perfect. Right there. Starting at 7 makes a 7 plus hydrogen.
All right, and that's why I wrote in Br2 over here. That's one of our diatomics. So all of this we're going to use when we're actually writing our chemical equations. So we're going to start by writing skeleton equations given the word form of the reaction. All right, so we're going to have to turn the words into formulas here. So our very first one, we have carbon and oxygen combine to form carbon dioxide. So we see to form, all right, so we might just draw in our yield sign here. We know that it's going to form carbon dioxide. Carbon and oxygen are our reactants. So carbon, we just write as C. Now you want to include the state symbol. What state is carbon? Well, hopefully you remember that carbon is a solid at room temperature. All right, and then it's combining with oxygen. So we have plus O2, because oxygen is one of our diatomics. Hopefully you all remember that oxygen is a gas at room temperature. All right. And those are going to combine to form carbon dioxide, right? So this is a molecular compound. There's no mono because it's not needed for the first atom, or for the first element. So we have C, 1C, dioxide, that's 2 oxygens, all right? That's fine. Okay. And then carbon dioxide, again, if we don't tell you what it is, it's because using common sense, you hopefully will be able to figure it out. Carbon dioxide, gas at room temperature. All right. On the second one, we're going to come back and balance these in a second. But our second one here, we have zinc chloride and hydrogen are formed. Okay, that sounds tricky. Those are actually going to be our products because they are what are formed, right? So if our yield sign is here, zinc chloride and hydrogen are going to be formed from the reaction of zinc and hydrochloric acid. All right, so we're going to start with our reactants, which here are zinc, right? So zinc, we have Zn, right? And zinc is a metal, so what state is it? A solid. All right, and hydrochloric acid, we gave you these acids in class to remember. Hydrochloric acid is HCl. Now, if we don't write HCl as aqueous, then it's not an acid. So we need to make sure that we add in the aqueous to signify it's been dissolved in water and it is an acid. Those are formed from a reaction of zinc chloride, right? So if we're writing zinc chloride, do you want to show them the crisscross method?
Yeah, so remember zinc is one of our it's one of our transition metals, but it's down here. It always has a charge of 2+. So we're going to go ahead and have zinc 2+, and what do we have? Chlorine. Cl is just 1-, and so we're going to crisscross and reduce. We don't need to do that, but we're going to have ZnCl2, zinc chloride.
All right. From a reaction of zinc chloride and hydrogen are formed. So we have solid and hydrogen. Remember, hydrogen is diatomic, so this is H2. Hydrogen is a gas at room temperature, right? Now our last one in a reaction, and remember when we write RXN over there, that is reaction. It's just shorthand for that. In a reaction, solid iron 3 hydroxide yields, there's my yield sign, solid iron 3 oxide and water, right? So Ms. Thomas is going to show you how to do the crisscross method of iron 3 hydroxide.
So remember, the 3 is telling me the charge of the iron, so it's going to be iron 3+, and hydroxide, you can find it on here, I don't know where it is, but it's OH-. Right down there, OH-1, so I am going to end up with iron hydroxide. Okay. So iron.
Right, now that's our only reactant, and we're given what state of matter it is there. It says solid, so we're going to write an S in for solid, and it's going to yield solid iron 3 oxide. Okay, so again, we're going to need to do the crisscross method. So we have, again, iron 3+,
and oxygen is always 2-. So we're going to end up with iron 3 oxide.
Fe2O3. Again, it says solid, so I'm going to add in my state symbol. You always need these state symbols. And water. So this is plus H2O. It doesn't say ice and it doesn't say water vapor, so we're going to assume this is liquid water, and we'll add in an L for liquid. All right, so that's writing the skeleton equations. Now the last piece, and we're going to come back to that board to balance, is actually balancing our chemical reactions, our chemical equations. All right, now why are we balancing? The main reason that we're balancing really is because we've learned about the law of conservation of mass, that mass is neither created nor destroyed in a chemical reaction. We can't lose mass, we can't gain mass. So when we're writing a chemical equation, we need to show that there's the same number of each atom on each side of the equation, right? So how to balance is we're going to add coefficients, right? Now, coefficients, not subscripts. If you look down here, I have 2 H2CO3. The coefficient here is that number out in front. This 2 and this 3, these little subscripts, are subscripts. So we're going to add coefficients in front of our atoms and compounds. Why? So that the reactants and the products have the same number of each atom, okay? So same number of hydrogen on each side, same number of carbon atoms on each side, same number of oxygen atoms in the reactants and the products.
It's very similar to when we balanced our nuclear equations.
Yes. Yep. Now, tips for doing this. 1, don't touch the subscripts. You cannot change the subscripts. 2, if polyatomic ions are present in the reactants and the products, then keep them together as one unit if possible. So if you look down here, you see NO3 in the reactants, we have NO3 in the products. You see OH in the reactants, OH in the products. You'll see when we go to balance those, we're keeping the NO3 together and we're keeping the OH together, okay? You're going to balance oxygens last, and you'll balance hydrogens second to last. These are just tips for how to make it easier. So oxygens can be if it's O2 by itself, or if it's an oxygen within a compound. Hydrogens, all right, it could also be H2. I didn't write that, but it could be H2, H2O, right? Hydrogens there, the H in HCl, the H in NaOH. So these are just tips. It doesn't always work out perfectly, but these are tips to make it easier. And then use the lowest ratio of all coefficients possible. So if you can, you're going to reduce.
If you usually follow these steps, though, and balance oxygen last and hydrogen second to last, you shouldn't have to reduce. It makes it faster, and you don't have to reduce usually. So that's always nice.
All right, we're going to do this one last, and we're going to we have a few minutes left, so we're going to race through these balancing a little bit. The way we're going to balance is on both sides of the reaction, we're going to make a atoms list. And you want to make sure it's in the same order on both sides. So we'll start with carbon, and we'll go with oxygen on both sides. And you want to figure out how many carbons and oxygens you have on each side. So Ms. Thomas will do the reactants.
Right now, I start out with 1 carbon on this side, and I have 2 oxygens because 2 are in each of my.
And I have 1 carbon here and 2 oxygens. 1 carbon on each side, 2 oxygens on each side. This is already balanced, so we don't need to touch it.
Basically, we have 1 mole of each of those.
Yep.
Okay.
Now down here, we're going to start with zinc on each side,
And then
then
I would do chlorine.
chlorine, and then hydrogen. So same order on both sides. And we'll start with the reactants.
Zinc, I have 1. Chlorine, I have 1. And hydrogen, I also have 1.
And over here, I have 1 zinc here. I have Cl2, so that's 2 chlorines. And I have H2, so that's 2 hydrogens.
Okay.
Now, if we're looking at this, do we have the same number on each side?
No. So basically what I'm going to do is I'm first going to look at zinc, and I'm going to say, okay, I'm good there. I don't need to add any coefficients right now for zinc. Then I look at chlorine before I look at my hydrogen, and I say, okay, hydrochloric acid, that's where my chlorine is. I need to get to 2. So what I'm going to do is I'm going to add a coefficient of 2 right here in front of this hydrochloric acid. So every 1 unit of zinc, I need 2 units of hydrochloric acid. That gives me 2 chlorines and 2 hydrogens, and that should work out okay.
Now we have 1, 2, 2, 1, 2, 2. And this is now balanced. Okay? The last one, in a reaction.
Do we have time for both, do you think?
Yeah, we'll go fast.
Okay.
We have FeOH3, so we're going to go Fe, then.
Uh-oh. Oh, yeah. So
Let's
our
do
OH
H.
actually stays together.
No, it doesn't.
You can treat it. It's going to be fast. Better.
Should we save it to the last one? Just because we haven't showed them that yet.
Yeah.
All right, so we'll do iron first. All right, so
I want to do hydrogen next,
I don't know why I did oxygen second. All right, so how many irons do we have on the left?
1.
Just 1. Oxygens.
3
3
whole oxygens and 3 whole hydrogens.
Over here, we have 2 irons.
It's hard to see.
We have 3 oxygens here and 1 over here, so that's 4. And we have 2 hydrogens, okay? Obviously not adding up.
So first, I guess I'm going to deal with my iron because that's what we decided to do. So I'm going to do 2 whole irons. Now that gives me 2 iron. That changes. I have now 6 of each of these.
All right, we're still not good. So if I look over here, my irons are good. I need to change something about our oxygens and hydrogens. Let's figure out the hydrogens. We're going to do them second to last. So I'm going to add a 3 here. Now I have 6 hydrogens. I have 3 oxygen here, 3 oxygen here, and I have 6 oxygens. All right, now, the very last problem we're going to do is keeping the polyatomic ions together. We'll do this really fast. All right, so over there, we're going to do both sides together.
1, 3, 1, 1.
1 aluminum, 1 NO3, 3 hydroxides down here, and 1 sodium.
Oh, we don't do. Oh, yeah, we do. Okay, so now I'm going to start with my aluminum. I'm okay. You actually want to add on that side.
3 here, so NO3 I have 3, Na I have 3.
So now I want to add a 3 here, and now I have 3 of each of these.
and it's balanced.
Boom.